This first one looks like a parabola, so quadratic. This one looks like a growth, so exponential. This one looks like a parabola roughly, so it's an upside down parabola. This one looks like a line, it's linear. This one looks like is that what you said before? You said exponential before the last one? Yeah, okay, it's like a decay, so uh-oh. Match each graph with a description. So an exponential function that is always increasing. What's another name for an exponential function that is always increasing? It's a growth, yeah. Which one of these looks like a growth? Is it F? Or is it down? Yeah, F. Hey, Marquise, you know that the principal sent out an email yesterday about hoodies to all teachers? Want to start? No, it's like a fashion statement. An exponential function that is always decreasing. That would be a decay. Which one of these is a decay? A quadratic function with a local. Oh, okay. So here we go. Back to the first semester. When you have a max, where should the parabola be facing when you have a max? Don't worry so much about the word local. And actually, local is not even that good of a word yet. That would actually, parabolas have what are called global maxes, but that's not that important. It should be a downward facing parabola. Yeah, downward facing. When you say max, what are you talking about? The vertex, sure. So this would be quadratic function with a local min. Yep. A linear function that is always increasing. How do you know that a linear function is always increasing? What determines what direction a linear function is going? The slope. Very good. So an increasing slope would be a positive slope. That would be B. And then the linear function that's always decreasing, that's a negative slope, that would be B. Any questions on that page? Go to the next page. Which is the only type of function below that has an asymptote when graphed? Yeah, that's really. I think this year that's the only time we've heard that, because there are other types of functions that have asymptotes, but I believe that's the only one you guys have been exposed to. Would be C. What is an asymptote? A point where your function approaches, a line that your function approaches but never actually reaches. Which is the only type of function that could have a local max? Yeah, B. Like a vertex. Describe the end behavior. Okay, so we've seen this before. But first, let's give them names. What name would go here? Yeah, this would be exponential. If you wanted to be more specific, we can call it an exponential growth if you'd like. But let's just say exponential. This one's quadratic. And this is linear. Who remembers what M behavior referenced when you're talking about M behavior? The arrows. What are the arrows doing? So remember, when you're talking about x going to negative infinity, this means what's the left arrow doing. When you say x is going to positive infinity, that's you're describing what the right arrow is doing. Okay. So what's the left arrow doing on this exponential function? It's going to the asymptote, which is at -3. If you don't put that, that's fine. I also showed you guys how to add a superscript, which is to say, since it's coming at it from the top, sometimes you can put a little plus up there, but you don't have to put that. What's the right arrow doing? It's going up to infinity, so positive infinity. Quadratics are easy because the end behavior is going to be both. It's the same for both arrows. Either both arrows go up or both arrows go down, and it's always going to go to infinity. So, what's in this case? What are both arrows doing? You got positive infinity, positive infinity. That's it. I agree with you, but okay. And you normally have lunch now? Mm-hmm. Try to go to lunch now and see if you can finish lunch, and then just go to regular advisement because it didn't really take that long. Here, what's the left arrow doing? It is going to negative infinity. What's the right arrow doing? Y positive. Which is the only function that might have n behavior such that x approaches infinity and f of x approaches 4, which exponential. Because why would the other two of those three, the other two have arrows that always go to infinity for the x, like they're going to go forever up, forever left, forever down, forever right. When would an exponential function be headed towards just a number? If that was the asymptote, right? And Reed gets it. Yeah. All right. Which is the only function below that might have this end behavior where it'll go left, up. Look at your paper because negative infinity x is left, y up, and then this is right, also up. So which one would have both arrows? What's the only one that could have both arrows possibly going up? Yeah, only quadratic. Because the other two exponentials and linear, they're going to have one arrow going up and one arrow going down. It just depends on how far up or how far down, depending on the asymptote. Okay, which of these would have, let's see, this is left, this is down, because y is going to negative infinity. This is right, x going to positive infinity is right, and up. So which would have one arrow going down, one arrow going up, but also going forever and ever and ever and ever and ever. Yeah, it could only be linear because with exponential you have to have an asymptote. Either the up or down would have a limit. So this would have to be linear. Which is the only function below that might have in behavior. So that we're going left, down, because y going to negative infinity is down. Then right, and then also down. So have both arrows going down. Only quadratic, because that's the parabola. Caleb, when I start hearing you be quiet, that means are you lost now? Or bored or what? Okay. Later on that you're confused. Okay. Based on this function, identify which description best fits the function. That's not based on the function given. Identify which description. It's like too simple. Like this is, even though you can't see it here, if I were to distribute this x with the x, it would become x squared, right? So which one's this one? What is this one going to be? Yeah, it's definitely going to be quadratic. Okay, fine. I guess if they want to know a local mix, min or max, this would be 2x squared plus 3x, where the key is the first term. That the first term determines the end behavior. So with a positive in front, is it going to be, are the arrows going up or down? Yeah, the arrows are going up. It's facing up. Therefore, the vertex is going to be a min. The vertex, like this parabola would look like that. So the vertex would be a min. Kiara, you following me? If we got on B, if you get rid of the parentheses, even without the parentheses, you're still going to have just the x is going to still be to the first power, even if you combine like terms. So what would this be? Actually, you know what? Let's combine like terms. 3 minus 4 is. You didn't have to, but it's definitely going to be linear, right? Now, even though we do not use the words decay or growth to describe linear, like at least not at this stage, but fine. Just think of growth as being a positive slope, and then think of decay as being a negative slope. If you remember y equals mx plus b, so you know where the slope is located. What's the slope of that line there? G of x is equal to negative 6x minus 1. Negative 6 is the slope. So is this a decay or a growth? The next one should be obvious because look at where the variable is located. Where is x located? It's on an exponent. Therefore, this is exponential. Now, what determines whether we have a growth or decay is the base. Since that base is between 0 and 1, is this a growth or a decay? This should be fresh in your mind. We just covered this. This is what we've been covering the last few weeks. Look at D. D also has the exponent, the variable up in the exponent. But now the base is greater than 1. So what's this one going to be? Growth. How about E? It's definitely quadratic, but even though the terms aren't in order, look at what's in front of the square, a -3. This parabola is going to face down. If the parabola is facing down, where's the vertex going to be? If we have a downward facing parabola, where's the vertex? A max. And then finally on the last one, that should be obvious, that's linear because we have the x to the first power. What's the slope there? What's the slope? The slope is 1/2. Do not say decay, because with linear, it's not about whether it's a fraction or not. It's positive or negative. That's a positive 1/2. Don't get that confused with exponentials. Slope is positive. On the one we did before, up here, the slope was negative. Based on, okay, these are going to be important. You're going to want to watch these. When you're given a sequence, these are all sequences, right? How would we know that a sequence is linear?
It goes up by...
Yeah, but if only that had a name. What was the name that we gave that? If there's a common difference, another word for that would be arithmetic. Okay? Arithmetic. How would we know that something is exponential? That is geometric, sure, meaning that we have a common ratio. The one that you do not know is quadratic. I'll show you quadratic. It's real simple. Okay? I'll just show you when it comes to it. Okay? Can we look at the y's here? Because that's the one all the x's. All we have to make sure about the x's is that they're going up in even increments. You can't be jumping around from like 0 to 2 to 8 to 27. Like they gotta be going in order, which all these x's are. But now we look at the y's, right? Do we have a common difference or a common ratio here, or none of the above? There is a common difference here of +4, +4, +4. So obviously this is linear. Okay. Is the common ratio, because the common difference we've made before, the analogy where it's like slope. So because this is going up, because the slope is positive, is it a linear growth or decay? But now here we go, perfect. Let's look at the one right next to it, right? You look at that one and you're like, well, I don't see a common difference there. I don't see a common ratio. Well, that must mean it's quadratic. Well, no, you never want to make that assumption. So if you want to know for sure how you get it, here's the way it should work. Treat it as if it was linear. Because of the three, the ones that are most kind of closely related are the linear and quadratic. The only thing that's changing is the exponent. And go ahead and take, this was called, what you just did over here, this is called taking the first difference. So take the first difference. You always gotta, remember, keep in mind, it's the one after minus the one before. So like, what's 2 minus 1? Yeah, like I went up +1. I went up 1. But then what's 1 minus 2? -1. What is -2 minus 1? -3. What's -7 minus -2? It should be -5. To go from -2 to -7, you go 5 down. Okay. If you wanted to prove that something was quadratic, what should be common is the second difference. You take the difference of the difference, and that's what ends up being common. So let's see here. What's negative 1 minus, like to get from 1 to negative 1, what should you be doing? Huh? To go from 1 to negative 1, you're going down 2. To go from negative 1 to negative 3, what are you doing? Going down 2. To go from negative 3 to negative 5, what are we doing? Say it again. Going down 2. So you see how we have a common second difference? The second difference is common. So that's what tells you that we have something that's quadratic. What's going to tell you whether it's a max or a min is what that common difference is. Because that common difference is negative, that means the parabola will be facing down. So is it going to have a max or a min? Okay, look at the next one. Huh? You just want to tell me the answer? Well, tell me what's the answer. You say growth? I don't see that. I'm not seeing exponential at all. Right? Because if it was exponential, there should be a common ratio. 0 times anything is 0. Like, so I'm not seeing where that would be exponential. It can't be linear. So instead of just assuming it's quadratic, let's test it for quadratic. Let's take both differences. What's the first difference between 0 and 2? Say it again. Plus 2. What's the first difference between 2 and 6? 4, and then 8, and then. Huh. Because then this would be 2, 4, and 8. Huh? But it can't be linear because linear would be yeah, the second difference is exponential. Huh. I want you to graph that? Because I'm not seeing exponential because the y's are times 3. Maybe because there's an asymptote, maybe that's what it is. That has to be it. There has to be an asymptote there or something. And we haven't done exponential regressions. Yeah, it has to be exponential. I'm trying to look for the pattern, doing it in my head. I'm getting times 2 plus 2. Like to get from one to the other, it's times 2 plus 2. Like what 0 times 2 is 0, but then plus 2 is 2. 2 times 2 is 4, but then plus 2 is 6. Yeah, so it has to be exponential then. It's just because it's an asymptote. The asymptote looks like it will be 2, but you're adding 2 at the end. So yeah, you're right. And because you're multiplying by a positive 2 to get from one to the next, that's what makes it a growth. If you were to graph it, I guess you would see it also. Okay. This one at first sight looks like it's going to be a parabola, but let's just double check. The first difference here is going to be minus 3, then minus 1, then plus 1, and then plus 3. 0 minus 3 is negative 3, negative 1 minus 0 is negative 1, 0 minus negative 1 is positive 1. But then when you take now the second difference, it's plus 2, plus 2, plus 2. So because the second difference is positive, it's an upward facing parabola. Which one is that going to be? Quadratic or linear? The vertex is at the bottom. Another thing that you could look at, I guess, is, I mean, maybe they don't want me to get this intricate into quadratics. Another thing you could look at is the y values. Notice how here the y values are going up and then they come down. It's a change in direction. They're like a parabola that's going up and then coming down. Here, the values are going down from 3 to 0 to negative 1, but then they go back up like an upward facing parabola. So like for instance here, another way, I guess if you wanted to simplify it, the whole thing with the asymptote, just move everything off. The point I was trying to make to you, but are these numbers all increasing, all decreasing, or is there a change of direction there? They're all decreasing. So they're all decreasing, that means it either has to be linear or exponential. But in order to be linear, there has to be a common difference. That would be the slope. Is there a common difference there? Doesn't appear to be. Because that first difference here is, what is it, negative 32, and then this would be here negative 16, and then this would be negative 8, and then this would be negative 4. So this is going to be definitely exponential, and since the values are going down for y, it's a decay. We won't worry about trying to come up with a progression and figure out what the exponential function is, but we can tell. If you look at it over here, this one, are the numbers always going, are they always decreasing, always increasing, or is there a change? It's always decreasing, but unlike the previous ones, here there is a common difference, which is minus 2. So this is going to be linear. Does that make sense? Did I confuse you guys at all with that third one? Okay. All right, perfect. So now we're ahead again. We're back ahead of. So we'll do as much as we can today. This might spill over a little bit until tomorrow. I think tomorrow I have to give back the test too, right? And then I don't know if we'll have time for the computers, but we've actually done this before. You did it in the first semester. What's another word for that? Slope. Average rate of change is slope. So in order to be able to do this, we need to remember slope formula. So let me write that somewhere here on the board. M is equal to y1 minus y2 over x1 minus x2. Whoa, Mr. Romero. I learned it backwards. It was y2 minus y1 and x2 minus x1. It's the same thing. So find the average rate of change from negative 1 to 2 for each of the functions below. Well, here's the good news. What type of function is a linear? When they ask you for linear, it's just slope. What's the slope there? And it's constant. Slope is always the same for all of those. So this would just be m equals 2. It doesn't matter what the points are. For the other functions, though, we are going to have to substitute. They want to know what's the average rate of change from negative 1 to 2. So we know that these are our two x's. So we just said x1 and x2. These are our two x's. It doesn't matter which one you want to call 1 and 2. Those are the two x's. I have to find the y's that go with it. So I'm going to have to plug in the y. So first let's substitute here b at negative 1, which would be negative 1 squared minus 1. Negative 1 squared is 1 minus 1 is 0. So one of the points we're going to have is negative 1 comma 0. B at 2 is 2 squared minus 1. It's 3. So we're going to have also then 2 comma 3. So now I need to go use slope formula with those 2 points. You can do slope however you'd like. I know which way I feel comfortable with. What's the first y I see there? And then the way I teach it is just remember that for the second coordinate to change the sign. So if my second y, my first y is 0, if my second y is 3, I'm going to write minus 3 over. What's the first x? Negative 1. My second x is 2. Change it to minus 2. That gives me negative 3 over negative 3, which is 1. Okay, now over here for c. First I need to plug in a negative 1. C, plug in a negative 1 would be 2 to the negative 1 plus 1. What's 2 to the negative 1? Let's see who remembers. But 1/2. Good. The negative flips it. So 1/2 plus 1. I guess just take my word for it. It's 3. Do you want to see me do LCD? What's 1/2 plus 1 is 3 over 2. You want to see LCD? Let's do LCD. Kiara, do you know that 2 to the negative 1 is 1/2? Do you remember why that was the case? The negative exponent flips the base. Okay. And then how would I write 1 as a fraction? How would you write 1 as a fraction? Right, you would look more cool if you just took the hoodie off completely. How do you write 1 as a fraction? Well, yeah, you could write it as 1 over 1, but thank you. That was a better way of saying it because that way I already have a common denominator. 2 divided by 2 is 1, so that gives me 3 over 2. So one of the points I'm going to have is negative 1 comma 3 over 2. Then when I plug in a 2, c at 2, that's going to be 2 squared plus 1. 2 squared is 4 plus 1 is 5. So another point is 2 comma 5. And I'm debating whether I should do fractions because I'm going to really mess with your heads. I'll do fractions. Why not? If you just want to do decimals, 3 over 2 is 1.5 if you feel like it. But I like to live dangerously. So my first y is 3 over 2 minus 5. I'm going to write 5 as 5 over 1 over my first x is negative 1 and then change the second x to negative 2. On the top, what's the LCD of 1 and 2? What is the least common denominator of the number 1 and 2? It is 2. So this stays as 3 over 2. This goes minus 10 over 2. 3 minus 10 is negative 7 over 2. And instead of dividing by 3, I'm going to multiply by the reciprocal, which I'm allowed to do. Dividing by negative 3 is the same thing as multiplying by the reciprocal. Now this allows me to say negative times negative is positive 7 over 6. If you would have used decimals, you would have been in bad shape because you would have gotten a repeating decimal. Which of these functions has the greatest average rate of change over that interval? So which one had the biggest change? And it doesn't matter if it's positive or negative, it's just what has the biggest magnitude. Yeah, in this case it was A, it was the linear one. Right? But all things being equal, like if you are ever asked about this, if you were to rank how much change occurs in any of these, it goes in order. These tend, if you give it enough space, exponentials change the most normally. This was a very restrictive interval, and also every function was different. Like they didn't really like how can I say this? Like here, this was a y-intercept of 3. This was a y-intercept of -1. That was no, actually, you know what? No, I take it back. It's not. No, the y-intercept doesn't matter. I guess more or less they were the same because of this 2. Here, this 2 was the slope. Here, the 2 was the exponent. Here, the 2 was the base. But if you would have given this more space, if you would have stretched out the interval further, maybe instead of going up to 2, if they would have gone up to like 50, you would have seen that the exponential would have blown the other ones out of the water. All right, see if you can do number 2 there. I want you to do all of them. Find all those rates of change. Luckily, you don't have to deal with the negative here. Okay, we'll do A together because that should be easy. Just look at it. What's the average rate of change for A? Huh? What's the average rate of change? What is the slope for this linear equation here? Linear function. Yeah, it's 2. For the other ones, you're gonna have to substitute because that's the slope. When it's linear, you don't have to use a formula. It's just you just look at the slope. Rate of change is slope. For the other ones, you gotta substitute. You already did it, Ed? Let me give everybody else a minute. Nakai, let me know when you finish. Nakai, you finish? Two. For these two, you have to plug in. First, I'm going to plug in a 2 and then a 5. So let's plug in a b squared 2. If I plug in, what's 2 squared plus 2? It's going to be 6. So 2 comma 6 is a point. Then let's do b at 5, which is 5 squared plus 2. 5 squared plus 2 is 27. So 527 will be here. When I do that slope, 6 minus 27 over 2 minus 5. That gives me negative 21 over negative 3, which is 7. That slope is 7. For the next one, C first at 2. So 2 squared minus 1 is 3. So the point 2 comma 3 is on here. And then for the 5, C at 5 is going to be 2 to the 5th minus 1, which is 31. So 5, 31. The slope is negative 28 over negative 3. That cannot be reduced. So that just gives me 28 over 3. Negative divided by negative is positive. So they want to know which of these had the biggest change. What's bigger, 2, 7, or 28 over 3? If you're not sure, divide 28 by 3. Get a decimal. That's going to give you 9 point something, 9.3. So what's the biggest number? Yeah, the exponential. The biggest change. And this just goes to show you what I just illustrated, which is, if you look at the intervals were actually the same. Okay. How much space is there between 2 and 5? 3 units. How much space is there between -1 and 2? 3 units. So actually the amount of space didn't change, but the thing is that this particular interval was very close to the asymptote. As a matter of fact, x is negative. When we plugged in, oh, I said I erased it. Like you see, the asymptote. Actually, I didn't erase it too. Both of these y values, 3 over 2 and 5, are pretty close to the asymptote, and that's when everything kind of compresses on an exponential. But now that I got further away from the asymptote, that's when the exponential function really starts to shoot up, and there's a bigger rate of change. In general, as x approaches infinity, so I mean that as you go further and further and further away, which one is going to grow at the fastest rate? Because that's exponential. Let's see if I can finish this page. Find the average rate of change between, okay, well, this one's not too bad because they give us a table, from -1 to 2. Okay, so here at -1, we have -1, -3. Is this one? Which one's the linear one? So we can knock that right out. The red, the green, or the blue? Yeah, the green one's the linear one. And what's the rate of change there? 2. So the other ones we're gonna have to find. So -1 goes with -3, and then 2 goes with 6. That one looks like it's gonna be the exponential one. So slope is -3 minus 6, -1 minus 2. Change the sign of the second. These both change signs. So you get -9 over -3, which is 3. And then on this one here, between -1 and 2, so that's -1, -2, and then 2, 5. So the slope is -2 minus 5, -1 minus 2, which is -7 over -3. 7 over 3. Negative divided by negative is positive. Which one of those had the biggest rate of change? What's the biggest number out of all those? 3. Yeah, the first one, A, which I believe that would have ended up being exponential. You know what? They probably, on all of these, they probably wanted us to name it. So this one was named A of X. So I think that's why we should put A of X. Let me see, did the other ones have names? Yeah. This first one would have been A of X. There's a linear one, and on the other one, there was C of X. C of X. Yeah. Consider the table below. This was a partial set of values based on the interval provided. Which function always has the larger average rate of change? Okay. So let's just see which one of these is the exponential one. This first one, from -2 to 0 to 3 to 7. Consider the table below that shows a partial set of values for 2 continuous functions based on the interval of x provided on the table, which always has the larger. I don't know about that, but okay. Let's not get too specific. Which one here is getting bigger faster? By the time you reach 2, which one has gotten bigger faster? Yeah, g of x. Find the average rate of change from 1 to 3 for the, okay, I guess we'll do that tomorrow. Yeah. Remind me then that tomorrow we'll start here. We have to do the test, and then if there's any time left, I'll have the phone books.